Hello, Zoom crew. Okie dokie. Let's go ahead and get going, folks. Okay, let's go ahead and get going for today because we have a lot to cover. So starting with announcements as per the usual, assignment 4 was due, actually it was due on Monday, but then you had an extension until Tuesday night. I think 8 people didn't turn in assignment 4. As a reminder, you can do a makeup exam, which is possible until December 7th. Today, we'll do a review of quiz 4. Then we're also going to be doing the future of game AI topic voting. In fact, that will be next. That's the very next thing we're doing. Then on Friday, we will have a practice quiz, and assignment 4 will be passed through the auto grader sometime by early next week. Some people have extensions, and I like to only pass it through once. As a reminder, this is the last time I'm going to say this. Demystifying Grad School workshop today, 5 to 7 p.m. You can check the slides for details. All right, future of game AI topic voting. As a reminder, these are the 8 topics. I will briefly talk through them. This is also maybe the only participation question for today. We'll see if I have time for a second one. Today is tight. A lot of stuff I'm trying to get covered today. We'll see. But let me 28. Hey. Real quick, so we have reinforcement learning in games, right? For that, I would basically do a high-level overview intro to reinforcement learning. What I can do in 50 minutes, talking about that being applied to games. For balancing game AI, that would be talking about how do you go about doing automated game balancing using game AI. So this is talking about future of game AI. So this would primarily be talking about how people are using automated game playing approaches to automatically balance content. AI for game design, that is going to be about how artificial intelligence can be used to help the game design process, like PCG, but more advanced basically, and trying to create whole games. Automated play testing, that is going to be related to 1 and 2. So there's ways that I can combine some of these lectures if they sort of get similar votes. But automated playtesting will include things like planning-based approaches for automated playtesting, pathing-based approaches for automated playtesting, etc. Automated game playing then is highly, again, related to automated playtesting, but this would, again, be more about sort of domain-specific approaches, which is primarily the way that people do automated game playing, but would also mean talking about MCTS, again, reinforcement learning, and things like that. AI-based game design, this is the one where it is sort of a focus of what if AI is the focus of the game design, so it's more of a design lecture. I find it's a helpful lecture to have if it's the very final lecture. So if this one gets voted on, I'll have it be the very last Future of Game AI lecture, because it's a good way to sort of summarize the whole semester, talking about all the different approaches that we've talked about. PCG via machine learning. So we're going to cover one PCG via machine learning topic on Friday, 2 days from now. But this would cover a whole bunch of other topics on PCG via machine learning. I have a whole grad course, so again, it's the amount of stuff that I can do in 50 minutes for this. And then generated dialogue and story. I don't know why dialogue is capitalized there, which is just what it says on the tin. So we're going to talk a little bit about generating story today, but this would be talking even more about these approaches. And I'll sort of hint at what that would look like. This should be set up so you can edit it. And also these numbers are in reverse order because I'm trying not to bias people given the vote spread that was before. But yeah, we're going to see what the top sort of 4-ish are, and then we'll cover those. If possible, I'll squish some topics together just to make it easier. Okay, so quiz 4 review. Let me jump. Oh, I can't, the mouse, there we go. All right. Any questions before I jump into quiz 4 review? Any questions on the future of game AI topics or what those would look like? Okay, cool. So let's do quiz 4 review. Let's try to go through it quick. So question 1, which of these would be the best overfitting definition mentioned in the regression and decision trees lecture? Who thought it was A, an overfit model is a model with poor predictive performance? Who thinks it's B, an overfit model is too focused on irrelevant elements of the training data? Okay, a lot of hands. Who thinks it's C, an overfit model performs above some fitness function? Who thinks it's D, an overfit model predicts a dog when given a cat? It's not D, I'm sorry. That was a specific example of where you were doing B. You were paying too much attention to specific details. Imagine at a big machine learning conference, every time we're talking about overfitting, we're like, oh, we always mean when you predict a dog when given a cat. I hate when my machine learning model does this on unrelated tasks. That'd be incredible. But no, that one was mostly there as a joke, and it is wild to me that it caught so many of you. But yeah, it's B. Question 2. Below is a set of comparisons between flow and drama management player models. Circle the most specific and accurate comparison. That's underlined because there's many of these that are true, right? So A is true. They're both player modeling techniques, but that's not the most specific and accurate comparison. Who thought it was B? They both require a large amount of tagging of in-game player actions. Right, it can't be that one because flow doesn't require any tagging. Both require designers to implement finite state machines or B trees. Right, flow doesn't require that. D, both involve altering player experience to more closely match an ideal. There's the hands, and that is correct. Question 3, which of the following is untrue of mixture models? So A, they allow for a final representation where each data point belongs to multiple clusters. That's just true. That's what mixture models are. So hopefully nobody said that. B, they can be applied to the same data sets one could apply k-means clustering to. That's true. So don't pick that one. C, they typically are the fastest clustering approach in terms of determining a final model. That is not true. It takes more time to be able to calculate a distribution, and they typically take more time to converge because they're more complicated. So it's C. Any questions on that one? Okay, and then finally, the one that was a little bit more complicated. There's a lot of stuff happening in this one, but the thing that actually matters is this last little bit right here. So let's say a designer decided to include Bartle's player types as well, a single type for each player in a match as part of the input to their model, despite the fact that these will likely not be all that helpful for this problem. So given that, what would be the best way to implement this to minimize any loss of accuracy? So A, no changes needed. A logistic regression can take Bartle's player types as input. That's not true. It has to have numeric input for a logistic or a linear regression. So no, not that. B, each player, Bartle's player type should be converted to some arbitrary number, e.g. killer 0, achiever 1, etc. The key to this one is arbitrary number. It should not be some arbitrary number. There is a way that you can input sort of individual sort of class-based information into a machine learning system. Generally, it's with a one-hot embedding, which we didn't talk about at all. But if it's arbitrary, right, then you're going to be telling the model things like, for example, achiever plus socializer equals explorer, which is not true. So this is not going to be it. C, they should tend to use something like a decision tree or random forest. Now, this is helpful for a number of reasons, right? It can handle the sort of different classes naively. And we already talked about how decision trees and random forests can deal with incorrect data, right? Or data that's missing. They're robust to that. So if it turns out that, in fact, as I said, the Bartle player types are not going to be helpful for this problem, it's not going to negatively impact the accuracy if we use a decision tree or a random forest. So it's C. Does that make sense? Okay. This is the one that a lot of people did get wrong. Some people did get it right, so I don't feel too bad. But question 4 is one that a lot of people got wrong on multiple choice. So don't feel bad if you did. Okay, question 5. So for question 5, the first part was really straightforward. You should just be using values from 0 to 25 inclusive, and you should not have the same value twice across any of the data points or variables. Almost everybody got this, except for those of you who, for whatever reason, completely ignored the instructions and just made up numbers arbitrarily. You lost points. Everybody else, you did fine. Question 5b would be the best clustering method for your data from Q5A. Why? So again, the thing that matters here is the why. Nothing else matters here. So you could tell me any clustering approach that we talked about that was a clustering approach. So that's single linkage, k-means, k-metoids, Gaussian mixture models, or just mixture models generally. You didn't have to specify. Any of those would have been fine answers. The important thing would have been why. So for single linkage, if the data was sort of in a like line-like setup, so if it looked like lines, right? Then sure, that could make sense, line segments. And then you could also have brought up the fact that for single linkage, we don't know k, and we don't know k for this data set, so that works out well. For k-means or k-metoids, you could talk about for k-means, the data is blobby, and it makes sense to take averages. For k-metoids, you could say, maybe we have something that's already close to a centroid for the things you've set up. That could work. For Gaussian mixture models, you could talk about how they're blobby, but you might have to have some overlap in the output content. Things like that. The only one that really stood out to me was one student that I marked who said k nearest neighbors. K nearest neighbors is not a clustering approach. Otherwise, I think basically everybody got this one, no problem. Q5C, give valid final clusters for k equals 3 using k-means, clustering your answers in Q5A. This one's pretty straightforward, as long as it's not the case that your any of the points would be in a different cluster than where you said they'd be. You got points here. So some people did lose points if you said like, oh, it'd be clusters, I don't know. A is 1, 2, 3, 4, 5, and then 6, 7, 8 or something. But actually 3 should have been in the second cluster or something like that. Make sense? But basically everybody got full points here. I was glad to see that basically everybody got full points for the clustering question. That was great. Okay. Question 6. So for question 6, I was asking you to design a player modeling systems for a virtual pet game, like a, I don't know. Now I'm blanking out all virtual pet games. There you go, Nintendogs, the best virtual pet game. Is there even still Nintendogs? Does that even exist anymore? Yeah. So for this first one, a model to map from a series of features that describe a player to a prediction of whether they will buy a new outfit for their pet or not. The big thing that people seem to be confused by was the fact that I said model, and then everybody thought that I went model-based player modeling. That's not the case. Machine learned models are also models. That was the indication here. Basically, none of the answers here would have made sense for any of the player-based, the model-based player modeling things. You all wanted to go data science on this. So for this one, and we're talking about mapping from a set of features to a decision, right? about whether a player will buy a new outfit or not. That's any classification approach, right? So we're looking here at decision trees. We're looking here at k-nearest neighbors. You could make an argument for linear logistic regression. It would depend on how you make the argument. Those are the answers we're looking at. For B, a model that can identify what groups of players exist within the game, this has to be some clustering approach, and you had to be specific. So you had to say, pick one of those 4 clustering approaches from before. It didn't work to say Bartle's player types because that wouldn't tell us what groups of players exist in the game. That would be us assuming what groups of players exist within the game. And then a model that maps from a set of features to how much real world money a player will spend in the game. This is some sort of regression, right? We have to go from information to a number. So again, you could do any of the regression approaches, linear logistic. You could do k-nearest neighbors, and you could even do you could even do decision trees. You could have said deep neural networks or any of these, but we didn't cover that. Make sense? Cool. Again, the thing that matters here is really the why, the brief explanation. Okay, question 7. Describe a situation where it would be better to use k-nearest neighbors instead of a decision tree. Never in my life have I seen so many students just copy pasting willy-nilly from the internet for this answer. It was pretty bad. A whole bunch of the people who decided to copy paste things for this answer did not get points because it was absolute nonsense, the things they copy pasted. In terms of what I was actually looking for here, right? I was asking you to describe a situation. You could make this as contrived as you wanted to. You could tell me, we have the perfect distance function, and it is always the case that the people who are the most similar to you according to this distance function have the same answer, right? But you could also talk about things like overfitting. You could talk about things like the representation potentially making more sense. Lots and lots of things you could do here, okay? Any questions on that? Question 8. So this one is about creating a data for a decision tree. Basically, everybody got points here, nicely, except in one case, a student decided to completely ignore this table as given and just create their own table with their own values. And then they lost a lot of points because none of them matched up. Question 8b, on the other hand, asked you to do a decision tree. The key thing here, well, there's a few sort of key things. One, you had to make sure that you had the best decision at every point, according to the metric that I gave you, right, which is up here. So some people ended up picking basically arbitrary splits, where they'd set it up so that they could have split their data like really nicely right at the start, and then they didn't pick that split, so they would have lost points for that. Some people also made use of comparisons I didn't allow. So I said you could use less than, greater than, less than or equal to, or greater than or equal to for your splits or choice nodes. A whole bunch of people just decided I'm going to use equal to, just straight up equals, and you lost a little bit of points for that one because that's incorrect. Some people also had issues where they would decide that something should be a decision node when it was actually not the case that they could have it be a decision node yet. So they might have a split, and then they would have it like 2 trues and 1 false here, and they just go ahead and put true immediately. Can't do that. All right, any questions on that? Cool. Then finally, the extra credit. So the extra credit has 2 parts. The first asks you to give a specific data point and what methods or models you would use to tag it. This is really key. That's why it's underlined. A whole bunch of people just described what data would look like or what it could look like for one player type, but they did not give me a specific data point. I was actually looking for like, what would the variables be that you would need to tag a player action as a particular type? So just saying like the number of times they killed something is insufficient. Because sure, that might be able to tell you, are they a killer or not, but they wouldn't tell you if they were an achiever, explorer, socializer. What I was really looking for was like the event, where did it happen, and then what variables you would need to track these different things. Then for the what training methods you would use and how you would produce the methods if you required training data. The key thing here is actually realizing you would need training data. So a whole bunch of students basically invented a k-nearest neighbor style approach, which is fine. But in that case, they would say often, I don't need training data. You still need training data for k-nearest neighbors. Otherwise, you can't start tagging things, right? It's all very well and good to say, okay, we'll tag things that are the most like these other players we've seen before. But unless we know their player types already, we can't tag them. The only time that you wouldn't need training data is if you had like a heuristic-based approach that said something like, okay, for these 4 player types, here's the ways that I would specify if that player action was one of these 4 player types. That would work for no training data. Otherwise, you did need training data. You would have to specify that a human or some other way of authoring that training data. Cool? Any questions on anything for quiz 4? Final call. Okay. Nobody in the Zoom chat? All silent there. Let me get a swig of water. And let's go ahead and talk about constructive PCG. So, as a reminder, on Monday, we covered search-based PCG. The idea of search-based PCG is that you're going to define a space where every point is an entity, and then you're going to search that space for the best possible entity. So we talked about greedy hill climbing. We used that to introduce fitness functions and neighbor functions. We talked about random walks, simulated kneeling, and then finally we ended on genetic algorithms. If there's time, I will do an extra example of genetic algorithms. And if there's not time, I'll do an extra example on Monday. Eventually, we will do more discussion of that because it's important. Today, we're going to cover constructive PCG. So as a reminder from last Wednesday, these are methods for building up PCG content piece by piece. So that's why I have Lego or Diplo or whatever that is represented on screen. Well, that's really low res too. That doesn't look that bad on my screen. That's just rendering really poorly. Incredible. So the idea is that we have slots, which are then filled by tokens and constrained by rules. All these things are authored by a person. So a person has to figure out where can slots go. A person has to figure out what tokens can go there. And a person has to figure out what rules are constraining the tokens. All of that's determined by a person. You can think of this as like a Mad Libs, if you ever played a Mad Libs. That's sort of the idea, but for arbitrary types of content. This is by far the most popular PCG method among actual game devs. It's used all the time, all over the place in game development. You might ask yourself, why is it so popular? PowerPoint just decided this slide was going to look like this. Compared to search-based PCG, right? It is more controllable. It is faster because it's generally one shot, and it is more intuitive. So it is easier to say, okay, what are the building blocks for building this thing than it is to say, what is a fitness function for describing what the best version of this is? And that's why it's used for all this stuff, everything on here, right? That's constructive PCG. So when it's used for spaces, this is like levels. It's generally either going to be used offline, which is going to be during development. So this is in tools for the game devs, or it's going to be online, which is in the game to do content live. Two major methods for these things. One is constructive grammars. So we talked about this a little bit last Wednesday. The idea is that you're going to be authoring chunks of a level, and then the rules for how those chunks can be combined. The other is noise, which are general rules for transforming random values into some sort of more structured input, and then using that more structured input as the output, rather, as the input to a PCG process. So constructive grammars, we talked about this on Wednesday, so it's just a little bit of a review. They're a type of generative grammar. It has a template with a series of slots, has a series of tokens that can go in each slot, and has a set of rules of how certain categories of token interact. You can use this, for example, for like a 3D adventure game, for generating content for that. So you can see, if we look at these maps, I specifically grabbed sort of high-level mini maps for a lot of these things because they're helpful. But you can see about how we have individual, whoa, where's my mouse? There's my mouse. You can see how we have individual rooms and then connective passageways between things, like individual rooms and connective passageways between things. We can think of these as like individual slots where each of these are tokens of things that can be placed in those slots. Now, none of these maps were generated with PCG, though the first one and the third one did an initial pass with PCG, and then they used a human designer afterwards. This one was all human all the time. But let's imagine that all of them were all PCG fully. In that case, we'd want something like this. We'd have a template. So our template says we're going to have an intro to our level, just one area that's like the beginning of it. Then we're gonna have a middle section, which is gonna be 2 to 3 sort of slots, and then an outro, the sort of final bit of the level. From there, we can say that we have these different tokens that can fit into each of these slots. In this case, I'm just using different shapes. We can think of these as being distinct rooms that have been authored by a human at some point. So our intro slots, our intro tokens are these, midsection tokens are these, and our outro tokens are these. We could have rules. So for example, the intro and outro connections, which are just going to use any flat surface and say that those can connect up, those can slot together, must connect to midsections. That's pretty straightforward, right? To be able to be playable at all, we would have to have it be the case that we could traverse from the intro to the outro. So if we do that, we could have an example output that looks like this. In this case, reading from sort of going from the bottom to the top. So this is the intro, this is the outro. You can see those sort of matching up. So we might think, okay, this is okay, but maybe not perfect. You have this weird dead end over here and this weird sort of like stifled dead end over here. This is possible to generate, maybe not the most exciting thing. So maybe then what we want to say is that midsections must be placed vertically, to say that we can't have these weird sort of dead end sections that we're going to generate. If that's the case, then we might get something like this. Well, in this case, we've gone from sort of 2 dead end sections to 1, 2, 3, 4, 5, 6 dead ends, right? That's not great. That's not ideal. So maybe what we actually want to do is slightly tweak that rule to say midsections must have at least 1 vertical section and 1 horizontal section. That way it can look a little bit more even. It's not just sort of a straight shot with a whole bunch of like useless corridors on each side. So in that case, it could look like this. This starts looking a little better. This starts looking more like an actual game map. Because you can imagine maybe you could even put something interesting over here so it doesn't feel so bad that you go into that section. But either way, it feels like you could sort of not just do a straight shot towards the goal, actually do some exploration, etc. But we could also get things like, say, this, using exactly the same rules, right? And this is no better than what we've had before. This doesn't look anything like a reasonable output map. So maybe we make one more tweak. We say each midsection can be used only once, because the big problem here is that we're using that plus looking midsection 3 times. It doesn't look particularly nice. So if we do that, then maybe we can get more interesting outputs, even if it's not perfect. So this is the sort of process you would go through when authoring a grammar like this for level design or any kinds of content, really. Checking to see what is possible to output, using that to tweak the pieces of the thing you can tweak. You're going to be doing a similar process, but you'll be tweaking fitness function and neighbor function and stuff for assignment 5. So there are some downsides of constructive grammars. So for example, there's no guarantee that they will create completable levels. Because we're doing this in one shot, right? We're just going from the beginning to the end, generally, of whatever our content is. There's no way to ensure that the content is actually good. We're not evaluating it at any point, right? So for example, and this is an example from Remnant from the Ashes, which released in 2019, I think. It was an FPS shooter, which was procedurally generated, and it was sort of Dark Souls-y. And it could produce areas, whole sections of the map that were entirely inaccessible. There was no way to get to them at launch. Now they could tweak that, right? But they didn't catch this, because with a PCG generator, you can create lots and lots of content and never see weird corner cases. And that's a big problem. The people at No Man's Sky, for example, authored automated bots to like check their generated content, because there's no way that a human could check all of it at scale. And so they use that to then try to change their editors and make it better. That's basically what I just said. And then you can take a lot of hand authoring of tokens to ensure level variety. This is really key. So it can often turn out that you just need a lot of human authored content to start getting stuff that feels like, oh, I'm just not seeing, oh, I see that section before, I've seen that section before, as you're moving through the sort of content. Okay, so that's grammars. Let's talk noise. So here on this slide to begin with, I have 2 kinds of noise. I have Perlin noise and I have value noise, but there's a lot of kinds of noise. The basic idea of noise is just local rules that are going to transform completely random, if I just like do a random sampling, to something that looks structured in some way. The nice thing about noise is that it can allow us to take content and then adapt it to specific use cases pretty quickly if it already looks like that. So noise, for example, sorry, Perlin noise. Perlin noise is used a lot for like mountainous environments because it already kind of looks like looking at a mountainous area from up above, right? So like Skyrim. Skyrim is Perlin noise. The landmass of Skyrim was generated with Perlin noise first and then tweaked by humans. So these were originally developed for texture synthesis, the idea of generating textures for 3D games. The reason why you would do that, by the way, is that very early on, they couldn't store textures, and so they had to generate them at runtime. Noise, as I mentioned, takes a random value on a grid and runs some set of rules on them to give them the appearance of structure. Kate Compton calls this flavors of noise. She's American, so that's why there's not a U in flavors. And then Perlin noise, which was originally developed for the movie Tron from 1982, is a favorite PCG landscape and basically has been since then. So, for example, I already mentioned Skyrim, but Minecraft is also Perlin noise. The areas that would be sort of the dark areas there become the water masses, and the higher areas, the sort of peaks, become the land masses, right? This is why, for example, you can queue in to a specific seed on Minecraft, you get the same thing every time. It's because the Perlin noise function is deterministic. And so what that key is to a particular area of Minecraft is just a particular lookup spot on this giant Perlin noise texture. And as an example, let's make that happen. It's going to take a second. I don't have to open Unity. I don't know when my camera froze, but of course, as per the usual, it froze. There we go. We're going to try to make a really crappy Minecraft map with Perlin noise if Unity loads. There we go. Okay, so let's take a look at what's happening at first. So I'm going to hit this play button, and we're going to get this. This is nothing, right? I'm going to zoom in a little bit so you can see what's going on here. We can see that we have very, very slightly different cubes of different size, but it basically just looks random, right? Now, what's happening here is that we have Perlin noise. You can barely see it. You can see it. There's sort of, I'm trying to get it so that you can sort of get a sense of this. The landmass here, let's get in really close, is like sort of slowly changing. That's equivalent, that's using Perlin noise from earlier, where it was, the darker bits are the lower areas here, and the higher bits are, the whiter bits were the higher areas here. That's basically what's happening. Let's take a look at the actual script. I'll just double click it. Light mode is probably going to be easier to read. Give that a second. There we go. Okay, so here's the setup. What we have here is just a start function. We're going to iterate for basically over 100 cubes, -50 to 50. Hello, I don't care. Ignore my prepared bake ahead of time. What we're doing is we're going to generate a cube, just instantiate a cube, and then we're going to grab a Perlin noise value. This is the Perlin noise function, right? And what I'm doing here is I'm grabbing from a particular offset, in this case 0, and I'm making some changes to that function. So I'm already dividing it by 5f. Let's just scale it down because the function is really, really big. It's giving us values that are changing very, very slowly, and we want them to change faster. Then I'm changing the cube's local height to be that Perlin value, and then I'm setting it at that position. Okay, does that make sense? Cool. Then what I'm doing is I'm picking a color, and I'm picking a color supposedly according to a Perlin value, but we can check in here, really it's just random right now. So a simple change we could make to make this a little bit more visible as to what's going on is to actually picking colors based on the Perlin value. So to be trying to picking these Perlin values these pearly values at this particular spot, in this case, like the pixel on that big textured image you were seeing earlier, and trying to match that up to a reasonable color. In this case, I have 3 colors, so I'm just going to map it up to the closest color that I can. Let's go ahead and run this version. So pretty much immediately, we can see that just by coloring things according to their Perlin noise value, their sort of height, we can think of it as that way. Immediately, this is looking more reasonable, right? We have a situation where, here, let me pause again and go over here. So we have a situation where the highest points are white. We can think of them as like white peaks, right? The other ones are these sort of gray blue, and then we have dark blue. We can think of this as like water, for example. But the amount of variety we're getting in our structures is still really low. It still looks mostly flat, right? So if we wanted to change that, what we could do is we could just increase the height of these Perlin values. So right now I'm just taking this Perlin value and setting it equal to the scale. What I can do instead is multiply this by some value. So what if I multiply it by, say, 5? We run that, and we're going to make all of the heights more extreme, more different. And pretty much immediately, right, we can see the effect of that, where we have like ridges and valleys. Now, this is not particularly smooth, right? Like each of these is just really, really chunky, but it looks okay. It's starting to look maybe a little bit better. But one thing we can do besides this, I mentioned earlier what we're doing here is downscaling and upscaling. So let me show you an example of that. I was dividing the Perlin values by 5, sort of the moving across the space and dividing by 5 to get a sort of more fine-grained detail. If I instead divide by 2, everything's going to be larger. You can see the impact there. We can see how it because the values are changing faster, right? Because I'm dividing by a smaller number. Hopefully that makes sense, right? The numbers go up slower if you divide by a smaller number. And because of that, we're just getting way more extreme things. Maybe this looks like kind of like towns or something, but I just think it looks like garbage. So let's not even go back to divide by 5 because I hate that. Let's go up to my pre-prepared dividing by 10. Run this again. There we go. That's starting to look pretty reasonable. So you can see how we have a much smoother look now to it, right? Maybe this is too smooth. Maybe we think that should be a little bit more intense. So in that case, what if we then also multiply this by 10? And then we get a values like that, which I think looks pretty nice. Now, there's a key thing here, which you'll note that we've seen like basically the same structures every time. That's because we've been using the same offset value every time. So if I change this to something arbitrary, like, I don't know, 100, for example, we're going to get a completely different map. Run this now. Looks totally different from what we were seeing before. We don't have that weird sort of symmetry that was happening in the middle there a second ago. But if I run it again, because I'm using the same offset, I'll get the same thing again, right? This is really handy because it means that rather than having to store a specific individual map, right, we can just store some specific keys, some specific offsets into this big texture. That's really handy for a number of different things. Okay, one last thing I want to show you, which is what if we go really small? So instead of divided by 10, what if we go divide by 20? What do we think is going to happen here? Any guesses? Please. Okay, we're going to think smoother. It's going to be super smooth. Okay, let's see how super smooth we're going to get, everybody. That, in fact, does look pretty smooth. So there's ways that we can tweak this even further, right? But you're right, because the numbers are increasing by an even smaller amount, right? That means that each cube is changing by an even smaller amount. It leads to a smoother appearance. So we could keep messing with this forever until we were getting structures that sort of matched our desired aesthetic, right? We could even be doing things like, for example, changing out the colors we're using. That's on cube. So you can see cube right now is using these 3 colors. If instead I really wanted like, I don't know, a volcanic mountain sort of aesthetic for some reason, I could instead change that color and we get this. I don't think that looks really nice. I'd have to change the other colors, but you know what I mean. These are the kind of tweakings that you'd be doing to working with noise. How we'd go from initially just random garbage to stuff that actually started to look closer to what we wanted to. And we got that, pretty quickly. That was what, like 5 minutes to look at something pretty reasonable. This is why people like working with noise. Nice and fast, and you can get something nice looking pretty quick. Okay. So noise. It can get something, as I mentioned, that looks okay quite quickly. It does require some expertise. So obviously I was cheating. I'd done this before and I had a value that I knew looked pretty good. And so I was heading towards there originally. But my first round of doing this was also pretty similar in terms of when I was first implementing this. But it does take some expertise to actually understand what's happening here and adapt it to your specific use case. Same with the grammar. There's also no way to guarantee specific criteria. So like how interesting it's going to be, how completable it's going to be. One thing you can do, and which was true in like some of the earliest games that use PCG, was they would find a whole bunch of interesting sort of offsets, interesting keys, and then they would just save those. And the player could only grab from those interesting ones. So it wasn't pure random. You couldn't get anything from within that space, just the ones they picked out as being good. So not only can this be used for game spaces, right? It can also be used for game scenarios. So like narrative, quests, etc. The basic way that this works is that what you're going to want to do is have a quest template. So for example, or a narrative template, a story template, right? We're going to have some like location slots. They could be filled with specific values, or NPC or enemy, right? Specific slots that can be filled with specific tokens. And then we're going to have the possible tokens that could fill those variables, potentially by looking at the player's game and saying like, okay, what enemies have you seen? What locations have you seen, et cetera. And then rules, constraints between variables that limit the types of values that can be placed in them. So potentially like, depending on a particular location, right, you might only see some kinds of enemies there. It doesn't make sense to have like, I don't know, a bear in a house, which Skyrim clearly didn't have that rule, but they should have. Maybe they should have. Maybe it's funny that there's a bear in the house. I don't know. So quest templates have been used by Bethesda, who makes like the Elder Scrolls and Fallout and so on and so forth. Now it's Sky, whatever. What's that called? The new one. If you know, you know. But the basic idea is that you're going to be collecting values like location, NPC, etc. once the player has visited them or been made aware of them. And then on generation, you just select a template, like a quest, like a bandit killing quest. And you'd say, okay, I'm going to select the bandit killing template, and then I'm going to fill it in with a location I know you know about, and an NPC that I know you've met. And that's it. That's generation. Quest templates are, basically Mad Libs. If you've ever done a Mad Lib before, it's just basically Mad Libs. Pros, they're going to be fast. It's just generative grammar, right? They can be customized to a player experience. And cons, they're basically Mad Libs again, where you do the same Mad Lib over and over and over again. So if you've done one of these generated quests, you've basically done them all. You know what it's like. So it gets boring really quickly. Now, this is actually very similar to what's done with music. So in music in games, most modern games actually have a procedural music system, which is that they queue in different tracks, right? We can think of the tracks as tokens, and what the player's listening to is a slot. And they're filled in with particular rules of like, okay, when things start getting intense, we replace the current playing music with the battle music or the climactic music, whatever, right? So most modern games actually have a procedural music system. More complex approaches do exist instead of just taking whole pre-authored tracks and like picking which one goes. Instead, you can do things like you have distinct tracks like bass, guitar, percussion, etc., and combine them in different ways according to a simple constructive grammar. So like, did anybody play Electroplankton? It's an old 2005 game, it's understandable. You were all children. But Electroplankton was this interesting, I think, DS game where it had this sort of more procedural system. And as you were sort of interacting in the world, it was building up this music track with you. Okay. Yeah, let's do PQ2. The possum is there as a hint. So what approach that we've seen already could we use instead of a constructive grammar? If we want to do something more interesting than a constructive grammar, quest or story generation in games, what could we do? And how would it work? Okay. Take a few minutes. think about an answer for the question. We'll talk about it. All right, let's see if we've gotten any answers. I can take my mouse. Thank you. Okay. Ignore the candidacy proposal from one of my students. Now let me close Unity because it's making my computer really slow. Here we go. Okay, one answer so far. Let's see if we can get another one. Yeah, MCT. A fun method. Monte Carlo tree. Just the one. You only get the one tree. It's just a joke. No trying to tease anybody. Okay, so somebody suggested rules. How this create a narrative or dialogue. The basic idea is you can have certain story, event, dialogue according to a text that is cut off. Hello? Hello, computer? Hello? Oh, I'm hitting that. That's why. Get out of your chat. According to a rule that the player has seen X object, the player has seen X, Y location. So for rules, I do think that you could do the generation of narrative or dialogue with rules, but it would very quickly be at something which is very similar to the quest template, where you'd need enough rules to like structure things in such a way that you were reproducing that. Or I think there's some other things you could do with rules that might be more interesting. MCTS. So I'm not sure about narrative, but it potentially generates some pretty unique quests every time. So I think you're getting closer thinking about MCTS, right? If we think about building up like pieces of narrative, right, or pieces of quests, then something like MCTS could be used to string those together. And then at the end could then evaluate using, this MCTS notion of simulation, how the player is going to actually play that quest, whether it's a good quest or not. So I think that's closer to what we might want to do. B trees, there'd be a lot of specific dialogues, since most of it we need to do by hand. So yes, I don't think this helps us generate because we just have to do a lot of authoring ourselves. Backwards or POV planning. Yeah, here we go. You could have goals, characters, etc., be nodes, and enforce a story. There we go. Now we're talking. So that's my answer as well. But actually, really, it's Fred Charles Merksavaza and Stephen Mead's answer. So the idea is to use planning, specifically hierarchical task networks, in exactly this way. By saying, let's just have agents take actions in the world, right? And then enforce story constraints on the final produced plans. So for example, they have some videos, which we're not going to listen to audio, but just, come on. Oh man, I could say 10 hours a week. Thanks. So in this example, I'm not going to play the audio. The audio is like computer generated text, but they tried to generate sort of like sitcom narratives by having each of these individual characters acting in the world with particular goals of like, for example, she was dating him. She just found out he was cheating on her, right? And then they all have particular goals of like, well, they don't want to be unhappy. They want to find love, etc. And then just basically letting these agents like go loose in the world and producing narrative from that. And then showing that narrative afterwards, once it's completed, as a way of sort of like generating narrative. So this is a common method. This is back in 2004, but this is like some of the earliest attempts at this This work has continued for the past, 16, 17 years. And now you can get some really interesting, really cool stuff out of running these sort of like planning-based approaches that you then have, a secondary system extract narrative from. This is called story sifting by many people. If we talk about the AI in games or AI-based game design, I'll bring this up in some more detail. The other example that's much more modern is Elsinore. Did anybody play Elsinore? I asked this before. Has anybody done it? No, okay. It's a cool game, especially if you know Hamlet at all. But the idea is that it's sort of like Majora's Mask Hamlet. You're going back in time as Ophelia, the main lady of Hamlet, and you're sort of changing the past, right? And then each of the agents are the actors of the play who are trying to do the play. Their goal is to do the play. And so they're going to try to keep doing the play as you're messing things up around them. You end up at interesting locations because of that. I was actually just on the call with two of the Elsinore devs last night. Okay, that is that. We don't quite have enough time for a GA example, so we'll do some more examples on Monday, along with some other wrap-ups of things we don't cover. On Friday, we are going to cover the sort of quote-unquote new hotness, it's now a few years old, wave function collapse, which is a PCGML method, a method for generating game content with machine learning that has been really popular among the indie groups. So look forward to that. That is it. Thanks a bunch. I'll hang out as per usual for a few minutes. Have a good rest of your day. Ooh, yeah, all right. This is just with cutting out the two middle layers. Exciting. I would still